Welcome to the lecture on melting and casting of cast metals. So, in this lecture we are going to discuss the foundry practices for the production of grey iron. So, in the last lecture we have discussed mainly about the varieties of cast irons, their nature. Now, we will discuss the foundry practices and some of the characteristics of the varieties of cast iron, and one of the main variety is the grey iron. So, we will discuss about it. So, what are the issues which are to be discussed while discussing the foundry practices when we melt and produce the grey iron castings? As we know that grey iron castings are used very extensively because of some of its remarkable qualities like good castability, good machining abilities and other things. So, we will discuss in brief the solidification of iron carbon silicon alloy system, because as we know that although the grey iron or the cast iron is normally of iron and carbon, but already we have discussed that silicon is one of the prime alloying element which basically controls the graphitization process. So, we will discuss the iron carbon silicon alloy system, because the presence of silicon basically induces certain changes in the iron carbon equilibrium diagram system. Then we have the graphitization during solidification and in solid state. So, basically what happens, as we have understood that when the carbon percentage is more than 2%, then in that case the carbon may segregate either as graphite, or we know that carbon will either be in the graphite state or in the combined form. So, the graphitization process will be in the different stages. One will be during the solidification stage, another will be when it is in solid state. Then also depending upon the alloying element and the cooling rate, the graphitization process takes place, and based on that basically the matrix structure is controlled. So, that also we will discuss. Chemical composition effects means the effect of the alloying elements that we have already discussed. What are the effects of different alloying elements like silicon, manganese, chromium or so. Then types of graphite flakes, because once we know that in cast iron the graphite is in the form of flakes. So, what are the different types of graphite flakes? Now, let us see the iron carbon equilibrium diagram. So, this is the typical iron carbon equilibrium diagram which tells that these are the different regions. As we know, this is the pure iron where there is 0% carbon, and then we move towards the varying percentages of carbon. Towards this end we will have the 6.67% where we have the formation of cementite. So, as we see, when we take, this is called the eutectic point, and this eutectic point is nothing but it has the, it has the property that solidification is at a constant temperature. So, this is normally in the absence of silicon, this carbon percentage for this composition is 4.3%. However, with the addition of silicon, the percentage of carbon requirement where this eutectic takes place, it changes. Now, because of this change, there will be depletion of carbon content, because there will be shift at this point and also at this point. So, all these points are shifted towards left. So, first of all let us see what happens in normal case if you have a composition of eutectic. As we know, this is the eutectic ledeburite composition, that is known as eutectic ledeburite, that is pertaining to this 4.3% of carbon. If we come to this side, if we have the hypereutectic composition, in that case you have the formation of So, as we move from here to here, then once we move, so we will have cementite plus liquid this zone, and then so cementite will try to precipitate, and once you are coming below this temperature, then you have for this you have eutectic ledeburite plus cementite. So, this portion will be eutectic ledeburite plus cementite. So, cementite will be on this side and the eutectic ledeburite at this composition. Now, as the temperature further goes down, so as we know this austenite which is here for this temperature, as the temperature goes down, we know that solubility of carbon in austenite also decreases. So, that also will lose the carbon. So, you will have this eutectic ledeburite, and then that further once it comes down, it is further transformed. So, you have cementite plus once it comes. So, graphitization takes place in the case of graphitizing elements, it will lose the carbon, and in the presence of graphitizing element, this carbon will transform to graphite, or if there is not that particular condition promoting the formation of graphite or graphitizing tendency is there, in that case you will have the formation of carbides. So, as we move down, then it is if so once you come to the temperature below this, you can see you have the formation of different phases like this. You have cementite plus transformed ledeburite. So, this will be perlite plus cementite. So, in this is basically when you do not have the silicon present. This is the equilibrium diagram for iron carbon system. Now, what happens in the case of silicon? Now, what happens in the case of silicon? This is the typical iron carbon equilibrium diagram when there is 2% of silicon. Wow. Now, what happens in the case of 2% silicon? We see that this eutectic point is shifted towards the left. So, what happens in the case of 2% silicon, this point as well as this point. So, earlier this was 2%, now you see it has shifted to this left. Similarly, this point also, this was 0.8%, this is the eutectoid point. This eutectoid point also is shifted little bit towards the left. What does it mean? It means that as the silicon percentage is increased, all these points, the eutectoid point, the point of maximum solubility for carbon in austenite, as well as this eutectoid point, all these points shift towards left, means they are depleted in the carbon content. So, if there is no silicon, in that case you are having this transformation of perlite. In that case it is happening, this austenite is having 0.8% of carbon, whereas once we have silicon as 2%, it goes below 0.8%. So, that is depleted. So, the carbide composition is depleted, the carbon basically. So, if you see that in that case, so that is why silicon is known as the graphite promoter. So, once the silicon is there, it will promote the formation of graphite. So, silicon if it is 4%, it will further move towards the left. So, basically on that there is a term known as carbon equivalent. So, because once you have the presence of silicon, in that case the point where this eutectic takes place, that changes. So, in that case the carbon equivalent is basically percentage carbon plus percentage silicon upon 3. So, that is basically the rule which tells that in the presence of silicon, this carbon equivalent will be changed. So, as we see, if the silicon percentage is 2%, in that case your 2% will be 2 by 3, so 0.67. So, basically a smaller amount of carbon only is required to get this eutectic point. So, with a smaller amount of carbon you get the carbon equivalent as 4.3. So, you need a carbon equivalent of 4.3, and for that in the normal case, in the absence of silicon, you need 4.3% of carbon, whereas in the case of having 2% of silicon, it will be 4.3 minus 0.67. So, somewhere close to 3.6% of only carbon is required to give you that eutectic composition, as is clear from here that you see close to 3.6 values, you have the formation of this eutectic point. Similarly, this point also shifts towards left, and this austenite is having lesser amount of carbon. So, once it transforms further, austenite will transform to perlite plus. So, this is transforming to perlite, this perlitic transformation will take place. So, this is basically depleted in carbon. So, basically what happens, the presence of this silicon changes the morphology of this changes the composition, it promotes the formation of graphite. Now, what happens in normal case when you have a slow cooling rate and you have good amount of carbon as well as silicon, both carbon and silicon are graphitizers. So, what happens, as we have understood, as we have already discussed, that you have the formation of flaky type of graphite, and this is the flaky type of graphite which is obtained in the case of grey iron. So, that is why grey iron is characterized by the presence of flaky type of graphites, and this flaky type of graphite may have the different kinds. So, different types of flakes are there, like type A, type B, type C, type D and type E. So, type A is the most desirable, which is uniform distribution and random orientation. So, we normally prefer to have this type A type of graphitic flakes, and this is the most desirable for giving you the best mechanical properties. As we know, this is the type B, which is known as rosette grouping type of graphite structure with random orientation. Similarly, this type C is known as the superimposed flakes type of graphite with random orientation. Type D is the interdendritic segregation with random orientation. We see that this is the interdendritic type of segregation, and then you have the random orientation here, whereas type E, it is also having interdendritic segregation type flakes, but it has a preferred orientation. So, normally type D and type E are not the preferred options, and the type A is the most preferred options as far as the graphite flakes type are concerned. Then now, once we go to the molding practices for the grey iron, you know, grey iron is normally done in the green sand molding practice. Mostly the green sand molding practice is adopted, and as we know, once we go for the sand molding, you need to have a better properties of the sand mold. So, all these properties of sand mold like green compression, shear strength, dry compression strength, permeability, moisture content, etc., all are to be properly controlled. Now, what happens when sand is heated to about 1500 degree Fahrenheit? So, in that case basically there is possibility of the sand metal reaction, and that is known as, so because of that there may be fusion of the sand particles on the casting surface. So, that fusion, that basically has to be minimized, but it is a process which is there, which is inadvertently it has to take place, and that has to be basic, that is why it has, the surface has to be cleaned. Now, to minimize that, to minimize this burning on, you provide certain additives like sea coal, gilsonite, coke, graphite, pitch, all these things are added as additives in the sand, so that this fused product which is formed on the surface is basically can be avoided. Regarding the grain size, as we know, the grain size will be and is normally represented by a number, that is grain fineness number. So, smaller is the grain fineness number, coarser is the sand particle. So, you have to have a proper size of the sand grains. So, if the sand grains are too coarse and they are larger in quantities like 6, 12, 20, 30, 40 or 50 mesh, means if they are coarser and they are basically making 75% of the molding sand, then you can have a coarse surface finish on the casting, as well as the metal may penetrate there. So, we know that the coarser particles are basically desired for giving better or they provide you better refractoriness, but then they give a poor finish. But on the other hand, if you take these fines or pan or 270 mesh, that is on the higher side, very fine particles, they are basically giving you although better finish, but then basically that provides a lot of difficulties, reduced ease of molding, and then permeability basically is very much reduced, and then accordingly the related defects like gaseous defects or others, or the expansion difficulties also may occur, because there is no void space in between them, so that the expansion can take place, that can be taken care of. So, these difficulties may arise. So, you have to see that you take the combination of coarse as well as fine sands. Foundry properties of grey iron. So, we will discuss about few of the properties of grey iron which has to be discussed while casting the grey iron. One is fluidity characteristics. So, as we know, this fluidity is defined as the ease with which a metal basically goes into the remotest corner of the cavities. So, without stopping or without premature solidification or premature its delivery at the corners of the casting. So, let us see fluidity. So, as we know, fluidity is measured by a test known as the spiral fluidity test. Now, if the fluidity is basically less, in that case you will not be able to completely fill the mold cavity. So, fluidity has to be at an optimum level. Now, in the case of fluidity, as you see, this is a spiral fluidity test where you see that this spiral casting is made, you have the sprue runner and there are standard dimension of these spirals, you have certain cross section and then it has, so there is certain gap also in between the spirals, and there is marking at inches of the spirals, and then once the metal, it is seen that at up to how many inches the metal travels. So, if the fluidity is more, the metal will travel to larger distances. So, that is known as spiral fluidity test. So, fluidity has to be good, as we know that most of the metals have good fluidity because the solidification is at a constant temperature. When there is a temperature range of solidification, then it also affects the fluidity. There are many factors which affect the fluidity, and in cast iron if it is of eutectic composition, certainly its solidification mechanism is just like that of pure metal. So, for that fluidity is better. Now, for finding the fluidity there are few terms. One is composition factor, and composition factor is basically defined as percentage of carbon plus 1/4 percentage of silicon plus 1/2 percentage of phosphorus. So, basically these three are the main elements which control the fluidity, and for that first of all this composition factor is found out. So, once you know the percentage carbon, percentage silicon and percentage phosphorus, then after finding the composition factor, this expression is further used, 14.9 times composition factor plus 0.5 times this pouring temperature T, that is in degree Fahrenheit, and then minus 155. So, this expression is used which gives you fluidity in inches. So, from this as you see that if the temperature of pouring is higher, the fluidity is going to increase. Similarly, your composition factor of 4.55 normally is known to have give you the maximum of fluidity. Now, what happens that when it goes even more, when you go to hypereutectic type of cast irons, as we will see later, then because of this kissing process, kissing phenomena, because there will be formation of the graphite initially. So, this carbon flakes, the graphite will initially precipitate out, and that basically, because being lighter, it will float. So, that basically known as kissing graphites, it will go on the surface, and that basically reduces the fluidity. So, it is maximum normally in the range of the eutectic composition. So, the fluidity is basically dependent upon the temperature, the composition factor. The temperature is high, then fluidity will be high. The composition eutectic, the fluidity will be maximum. So, once it goes above the eutectic point, that is hypereutectic case, there also fluidity decreases because of the kissing process, because of the formation of this graphite which is occurring. So, then you have the shrinkage characteristics. So, as we know, there is always shrinkage when there is solidification process. So, when we are converting the stage from liquid to solid, then there is shrinkage. Now, solidification shrinkage is normally defined as 2 times percentage of graphitic carbon minus 2.8. So, this is the solidification shrinkage, and that is delta V. So, this volumetric change. Now, as we see, the graphitic carbon is basically controlling the solidification shrinkage in case of grey cast iron. Means, if this amount is 2.8 or more, in that case it will be positive, and so its value can be positive or it can be negative. So, the percentage total carbon will be defined as percentage of graphitic carbon plus percentage of combined carbon. As we see that you have total carbon, in that you will have the graphitic carbon plus you have the combined carbon, that carbon which is in the form of cementite. So, for a larger value of this graphitic carbon, in that case your volume change, it may be positive, because if it is more than 2.8, the volume change will be positive. So, for ordinary grey iron, where you have 2.9 to 3.1% graphitic carbon, in that case your rising is not needed for the purpose of solidification shrinkage, because in the case of grey iron with larger amount of silicon, the graphitic carbon becomes more. So, in that case your, because as we know that once you have silicon, the combined carbon amount is less, because the curve is shifting towards left. So, in that case that point, so combined carbon becomes less in those cases, and graphitic carbon becomes more when you have the presence of silicon, and once you have that, the volume change is basically positive, and in that case you do not have the riser requirement in case of the grey irons. That is why sometimes it is also known as riserless casting. So, in those cases you do not need the risers for that process, although riser is required, so that there is pressure applied, and to get the sound casting there will be riser, but then you are not very much thinking about the requirement of riser for supplying the extra metal because of this volume requirement. If graphitization is complete, percentage of total carbon and percentage of graphite carbon are certainly equal, because if the total carbon is changing to graphite, it means complete total percentage carbon is nothing but the graphitic carbon. On the other hand, if it is not at all any graphitization, so percentage of total carbon is the combined carbon. So, no graphitization has occurred, it means percentage of graphitic carbon is 0, So, there is total carbon is nothing but the combined carbon. So, about 0.5 to 0.8% of combined carbon, if it exists in the grey iron, it generally indicates that microstructure is largely perlitic. So, once you have the 0.5 to 0.8% of combined iron, as we know that when in the absence of silicon you have 0.8% of carbon for the ductile composition, and once it cools under normal conditions there will be perlitic matrix. For white iron, if you see, if you look at this, for white iron you do not have graphitic carbon. So, what you see is you have about 0.6% of volumetric shrinkage. So, that is why in the case of white iron you see you have the requirement of risers. Although riser is required, as we discussed, for the riser pressure which is required to give you a sound casting. There is a important treatment, that treatment is known as inoculation treatment. So, inoculation treatment is nothing but the treatment to give the better nucleation of graphitic flakes. So, it is used to establish nucleation centers for precipitation of graphite into small type A flakes uniformly distributed in the matrix. So, basically you have the nucleation of graphites, and for its better flakes and type A flakes this inoculation treatment is done. So, what happens if you have the better inoculation treatment and better nucleation of graphite, better type A flakes are formed, in that case you are getting the better mechanical properties. It also basically minimizes the undercooling. So, the undercooling is basically minimized, and because of that you have the graphitization tendency further promoted. If there is more undercooling, in that case you may have the chances of the formation of white carbon. Then you have the reduction of iron carbide and control of graphitic structure. So, what is the practice? The practice is that inoculation may be done in the ladle or in the mold. So, in the ladle you give the inoculants and then bring it. You may have the use of tablets. So, basically these inoculants are in the form of tablets, which are normally the ferrosilicon is used as the inoculant, and where the silicon is normally 72%, manganese, calcium and aluminum 1 and 2% and 4% of iron, basically they are bounded with stearic acid. So, then you are making a tablet of it and then you are putting into it, and then you also do the inoculation in the mold, so that if there is any further fading off or any fading of the pouring inoculation, then during that process of going into the mold, then in that case it can be compensated. So, for that also we do the mold inoculation. We also do the heat treatment of grey iron to get the improved properties. So, the properties which can be improved by the heat treatment process are the improved machinability, wear resistance, strength and stress relief. So, as we know that for getting the improved machinability you will have to go for annealing treatment, where you heat and then you are cooling, you are holding in the furnace and then cooling slowly. So, in that case your machinability is improved, it becomes soft. For wear resistance, if you heat and then do the normalizing treatment, allow the specimen to cool in the air, in that case you get the better wear resistance. So, normally for the piston rings you go for such treatment. For getting the strength you go for the quenching treatment, you heat and above the transformation temperature and then cool in or quench in the water or oil. So, you get the better strength. You also do the stress relieving treatment below the lower critical temperature, holding it so that the stresses are relieved. So, these are the different kinds of heat treatment processes which basically modify the properties of the grey cast iron. Thank you.